So let's go ahead and talk a little bit about the oxidation of alcohols. So we've already learned that it's possible to take carbonyl compounds, that is to say, compounds that have the carbon double bonded to oxygen, and we can reduce them down with reducing agents, or if we don't mind, or that is even to say require for the target we're trying to achieve, a transformation in the skeletal structure, then we can also do a Grignard reaction and take a carbonyl and turn it into an alcohol. But more commonly, if you want exactly the carbon structure that you have with the carbonyl, then you'll use some of those reducing agents that we talked about on Thursday, such as sodium borohydride or lithium aluminum hydride. But it turns out there is a set of reagents that can actually do the reverse. It can actually take an alcohol and oxidize it into a higher oxidation state. And that can be an aldehyde, that can be aldehyde, a ketone, or a carboxylic acid. What we're going to find is primary alcohols typically transform first into an aldehyde, and then they undergo further oxidation to a carboxylic acid. And part of that reason, as we're going to see in a moment, is one of the fundamental aspects of these reactions, even though their mechanisms vary a little bit, they all involve in one of the last steps where the further oxidation occurs. They involve a removal of one of the protons connected to the carbon that's alpha to the oxygen that's becoming the carbonyl. So because the aldehyde still has one, it's able to undergo further oxidation to a carboxylic acid. Now, as we're going to see, it depends on the conditions. Now, ketones, regardless of the conditions that we're going to talk about with regard to stopping at aldehydes or not being able to stop at aldehydes, most of the reagents we're going to see, they will take the secondary alcohol with the single alpha hydrogen on it and transform it into a ketone. And then what we also find is tertiary alcohols undergo no oxidation. I suppose if you really heated it with really strong reagents, maybe you could rip it apart. But really, with most, most standard alkane type structures, you're not really going to be able to do that. We'll see in chapter 17 when it comes to carbons that are connected to benzene rings. The benzene ring is able to actually activate the carbon such that it can actually undergo such a strong reaction, oxidation, that it can transform despite the additional carbons there. Although we'll find that, actually I take that back, even in that case we'll find without a proton on that carbon, oxidation just can't take place typically with most reagents that we're going to be familiar with here in organic chemistry too. So the most common oxidizing agent that we're going to learn about is chromic acid or chromic acid derivatives or things like chromic acid. Now, it's the most common because it was one of the earliest reagents. It's also known as the Jones reagent. The thing is, although it's common and useful, it can be quite dangerous because not only is chromic acid strong in its acidity, it's also quite carcinogenic. And so it has a toxicity that's not the greatest. And so we find that in organic chemistry, they really do try to phase out the use of chromic acid when possible. But it really does help us understand some of the mechanistic and, just some of the aspects of oxidation that really explains this thing that we're going for, which is how do we stop and control whether we get an aldehyde or a full-on carboxylic acid as we undergo these oxidation reactions. And also, there isn't one set of reagents. You can start with chromium trioxide, and in the presence of a strong acid water source and acetone, or you can add sulfuric acid and water to sodium dichromate. Both of those eventually lead to chromic acid. And the chromic acid, as we'll see in a second in the mechanism, is really the key thing. But you're not going to write chromic acid directly into your reagent spot or see it typically, because chromic acid it's not generally the reagent that you just reach on a shelf for. You generate it with one of these combinations. So either you'll see chromium trioxide with H3O plus and acetone, or you'll see sodium dichromate with sulfuric acid and water. Now keep in mind, you do have to have all of those reagents present, either this set or this set, in order to actually cause the chromic acid to form and thus cause the oxidation. So it is important that when you as you'll see in a second, let me see if I find, not yet. But if you do use this for an oxidation, you have to include these two things and this in the arrow of your reagent, in that reagent spot on the arrow for whatever reaction you're indicating. Now, let's take a look at the mechanism. It's not a full mechanism. As you can see, we're just talking about two stages, not steps, but stages. And in the first stage, the alcohol interacts or reacts with the chromic acid molecule and forms a chromate ester, probably through a series of mechanistic steps, but we're not going to delve into those steps. But it is important to realize it's the alcohol that will do that. You have to have a carbon with an OH group that can react with the chromic acid to form this chromate ester. So that is the key. And now you might be asking, why does aldehyde do it? It's not an alcohol, and we'll mention that in a second. Now, in order for the oxidation to take place, you do have to form this chromate ester, because that's where the alpha hydrogen is removed. The hydrogen on the carbon that has the oxygen, that used to be the alcohol, that hydrogen is going to be deprotonated via essentially an E2-like mechanism. It's the alpha hydrogen is going to be, alpha proton is going to be deprotonated. The electrons that once held onto it are going to fall onto that oxygen, and then since oxygen is period 2 and can't have more than 8 electrons, what's going to happen to those other electrons that are connecting it to the chromium atom? They're going to fall off onto the chromium atom, because metals, metals are somewhat, gain electrons. They are reducible. And so those electrons easily fall onto chromium and just reduce it, gain electrons reduction. And so chromium's undergoing reduction as this piece of the molecule is undergoing oxidation. That makes sense if you think about our general chemistry knowledge. If something's undergoing oxidation, something else has to be undergoing reduction. It always happens in pairs. That's why it's called a redox reaction. So that's what happens. There's a deprotonation step where the alpha hydrogen is deprotonated that forms that double bond in that oxygen. Now, why is it that it continues? Well, let's not talk about that. How do we make it stop? Well, I guess actually we do have to explain this. So how do we stop in an aldehyde, or why is this all happening? And the reason is because these reagents that we just talked about here have water present. This H3O+, if there's H3O+, that means there's some amount of water present in solution. Right here, this H2O, that's water. And so when you're under aqueous conditions, so both of these are aqueous conditions, what we find is aldehydes, and we'll talk about this more in chapter 19. Where is it? Here we go. Aldehydes undergo a reversible reaction where they form this geminal diol structure. So a water molecule in the solution attacks this carbon, just like we talked about with the Grignard reagents that are strong nucleophiles, and the hydride hydrogen from the aluminum hydride or the borohydride. The water molecule is able to attack this carbonyl carbon like a nucleophile and move these electrons up, and then there's some protonation, deprotonation steps, and you get to this diol. So an aldehyde under acidic aqueous conditions can transform, even if not a lot of it, some of it in equilibrium transforms into a geminal diol. And so that geminal diol, one of those OHs, is able to form the chromate ester. So now one of the OHs has become an oxygen that's bound to the chromium of the chromic acid. There's another OH located on that carbon, and then there's still that alpha hydrogen. So one of these would be connected to the chromate. That's not a complete thing, but there's a bunch of stuff here. And this hydrogen here will eventually be deprotonated, bringing these electrons up. These electrons fall off of the chromium, just like we saw in this step right here. And so that is how aldehyde can undergo further oxidation under the aqueous conditions. So that's why you can't stop in an aldehyde. Under those aqueous conditions, it turns into, even a little bit of it turns into a geminal diol and quickly then undergoes further oxidation. So it's really hard to try to isolate an aldehyde. You don't do it. You don't try to do it with aqueous chromic acid reagents. Instead, if you're going to use those, you're going for the carboxylic acid, assuming you're starting with a primary alcohol. How do you stop at the aldehyde? There is another way, another set of reagents. They're still chromate based. In other words, it still is the same mechanistic principle where you're going to form a chromate ester, and you're going to cause that chromate ester to undergo elimination at the alpha proton and do all this stuff. But notice for this reagent, no water. The solvent, which is right here, dichloromethane. And that's because this is a organic, it's not really organic. It's a, it's an organic cation and then a chromate, chlorochromate anion salt that is soluble in dichloromethane. So there's no water present, which means the aldehyde that forms will not turn into a geminal diol. And since this aldehyde cannot transform into having an OH group on it, then it cannot form another chromate ester and undergo further oxidation. So that's how we control this. It's not really the reagent that actually does the reaction, that is the chromate, that's different. It's this reagent setup here still involves chromate, some type of chromate structure. It's the idea really that there's no water present. Without water being present, it's also not acidic too. You might notice it's actually more of a basic solution. But without water and without being under acidic aqueous conditions, the aldehyde cannot form a geminal diol, which means you cannot form another chromate ester. And thus, this proton will never be able to be deprotonated in a mechanism like this, leading to the carboxylic acid. So it stays an aldehyde. So that is how you can make an aldehyde from a primary alcohol. These, once again, one of the other issues, as I talked about the first day of class with organic chemistry, is understanding the explanations of why things happen, as we just talked about here. Knowing how to kind of determine what product happens when you know the reagents, so single step transformations. We have a couple of these now that we've talked about, how to turn a primary alcohol into an aldehyde, how to turn a primary alcohol into a carboxylic acid, and how to turn a secondary alcohol into a ketone, which it turns out any of the oxidizing agents we're going to learn about in this section whether they're the aqueous, acidic aqueous ones, or the PCC and CH in the dichloromethane, or some of the two that we're going to learn more in the main the lecture on Tuesday, which is SFERN or DMP. Those, if they're in the presence of a secondary alcohol, will still react with the secondary alcohol and form the ketone. It's just, You can also do it with the acidic chromium. So they all transform secondary alcohols and ketones. The main difference is if you're doing a primary alcohol, some of the reagents take it all the way to a carboxylic acid and others stop at aldehydes. And that's a useful thing to know because sometimes in our synthetic pathways, when we try to do a retrosynthesis, we may want to either end on one of those, aldehyde versus a carboxylic acid, or it might be one of our intermediates. So I think that's it. Yeah, that's for our lecture on Tuesday in class. So I will see you guys on Tuesday. Hopefully this is a good introduction to the fundamentals mechanistically, and even having these various now new tools in our synthetic toolbox. And I will see you guys in class.